So welcome everybody to the analog work group. I appreciate everyone making time today to join. So it gives me great pleasure to have Professor Sahin Sapnagar from University of Minnesota be with us today with his colleagues. They're going to be talking about the work that they are doing online. It sounds like very promising work, and I think would be of great interest to the analog work group. So with that, why don't you go ahead and take it away, Sahin.
Okay, thanks, Rob. Let me share my slides, which for some reason don't seem to be showing up. Just give me a minute, please.
Yeah, take your time.
Here we go. Okay, so thank you all for being here. This is a presentation of the Align project, and we have several people from Align who are on this call today. The main presentation is going to be made by me, followed by Steve Burns and Sona Rialdes. And in addition, we also have Ramesh Harjani from the University of Minnesota and Jiang Hu from Texas A&M University, who are kind of faculty members who are leading the Align project, and they have their own students working on it. So like several such efforts, this is supported in part by the DARPA IDEA program. And the idea here is, again, this is probably a very simple motivation for an analog work group. There's analog everywhere. Interaction with the real world is all analog. There's much more analog content on chips these days. And it's really been the last frontier in design automation. It's been really hard to automate analog. In part, this is because of the difficulty of the problem. In part, it's because it's cultural. But really, we need to get all of these things to come together. And this is sort of the perfect storm right now because there's funding to do this. There's interest from users, and there's the need from the design side as well. A couple of points before I move on. I don't want to spend a lot of time belaboring the point to this audience, but basically one of the things is that analog is a small part of a larger digital system, but in terms of design difficulty or respins, it's actually considerably a major bottleneck. So as you can see in the picture on the left, the design risk is shown over here. It's an inverse proportion in some sense to the area occupied by this. And a large number of respin issues have been reported to be AMS in nature. Now, the problem that we are tackling here is automated analog layout. So typically, your designer, who's an intellectual, basically designs their circuit on a napkin or something like that. This is a beautiful graphic from Rob Rutenbar. And then somehow this has to be taken by a layout engineer to something like this. This is, of course, a gross oversimplification. In between this, there's a bunch of other steps, topology optimization, transistor sizing, etc. But this really, the layout generation part is an extremely time-consuming part. And this is the part that we are trying to alleviate in this project. So why is layout important? If you think about the overall design cycle, there is, like I said, the circuit designer part on this side shown in red, and then the layout generator, which often takes days to weeks. And then once you get the layouts, the circuit designer basically proceeds on assumptions or coarse estimations of parasitics. Once you have a layout, you know what the actual parasitics are. So this might mean that you need to re-optimize the circuit based on better parasitics, then you perform the layout again, and then you go through a set of multiple cycles, and the overall process can take weeks. So if we could somehow shorten this to perform layout in an automated way and complete it within minutes or hours, this would really be great, because what it would mean is that I could estimate my parasitics very quickly. I could shorten the optimization cycle. I could perform, in principle, even more optimization cycles. And in fact, this means that parasitic estimation could be done efficiently using fast layout, for instance. And the goal of Align is to perform efficient, automated, high-quality layout synthesis. So now, people have been looking at analog layout for a really long time. In fact, Professor Harjani, my colleague on this project, worked on this for his PhD thesis in the late 1980s. And his work was a pioneering piece of work because it got a Best Paper Award at ICCAD, I believe. So people have been looking at this for a long time, but it's really had a lot of resistance from industry. So the things that are different this time are the following. The first, as I said earlier, is the fact that people are more ready for it. And one of the reasons they're ready for it is because we are going into FinFET designs these days. Now, in the old days, designers had a lot of degrees of freedom. They could route in kind of clever ways, etc. But with FinFET design rules, there's almost freedom from choice in the sense that you can go in a reserved layer in the bottom layers, for example. You can't really do kind of really messy things. And this becomes very hard for a human designer, but it reduces the search space for a design tool. The other thing that also happens is that the constraints could potentially be expressed more clearly. Now, one of the things that we are trying to do in Align is to be a sort of a general purpose layout generator. So we're not targeting just data converters or just filters or just operational amplifiers or anything of that sort. We're trying to address a wide range of analog circuits. And we think of them in terms of 4 broad classes. One is low frequency analog. You can think of these as OTAs, for example. Wireline or high-speed link circuits, and these are things like DLLs, PLLs, VCOs, clock data recovery, etc. There's wireless, which is RF circuits, so all components, LNAs, mixers, etc. And then power delivery circuits, such as LDOs or voltage regulators of some sort. Now, when we think about this, there's a kind of a taxonomy of constraints that we put together for this. So for example, this table over here on the y-axis shows the list of families of circuits. On the x-axis, it shows a set of kind of things that you might worry about. And depending on the class of circuits, there are different things that are starred that are really important, and things that are in light colors are really not that very important. So really, one of the things to go from kind of a special purpose layout generator, which has been around for a long time, to something more general purpose is to capture this relationship more clearly. The third thing is that in recent years, there's been a lot of advance in machine learning, and we've been trying to exploit that in several of the steps of our approach. I won't be able to talk about this in a lot of detail today, but these are some of the things that are helpful because now you have freedom from choice. We have a methodology for being able to handle a wider range of circuits. And we can actually exploit machine learning, which wasn't available even 5 or 10 years ago, let alone 30 years ago. Our approach is kind of really heavily driven by FinFET technology nodes, but we have also built designs in bulk node 65 nanometers, for example, and we are currently targeting Skywater 130 as well. So even in the FinFET world, I talked about freedom for from choice, but things are still pretty hard because just kind of having freedom from choice, quote unquote, is a gross oversimplification. One of the issues is that this is data from an Intel paper at ICCAD. If you look at the gap between schematic and post-layout simulations, schematic simulation predicts a performance of something like this. Post-layout simulation predicts a performance that's kind of much further away. So that gap is kind of further. So this means that the design cycle actually becomes more complicated, and having a fast layout generator is extremely helpful. The second is from the layout standpoint itself, you have many more and more complex design rules. So this is an example of a hypothetical design rule violation, which is typical in many technologies, where, for instance, it's not just the distance between VRs, but it's the VR density and diagonal distances, and also some kinds of Boolean relationships between structures that need to be incorporated. A third factor is that if you look at FinFET technologies, they're very prone to self-heating because you have these long and high fins. So you can call it FinFET, Trigate, whatever. You still have a lot of thermal concentration over here, and that needs to get out to the ambient. That causes self-heating. It causes performance degradation, reliability degradation, etc. So these constraints have to be taken into account during layout. Moreover, if you think about interconnects, they become smaller and smaller, narrower and narrower. And this means that your per unit wire resistance, especially in lower metal layers, is pretty high. So as a result of this, things become kind of pretty complicated because in order to maintain performance, you need to make sure that wire resistance is not a bottleneck. So in fact, in many cases, we find that in order to meet performance, we need to use multiple parallel wires in lieu of wider wires because of pitch requirements, especially in lower metal layers. So that's the motivation. This is a big picture view of Align. So our input, in principle, when we started, the directive from DARPA was to start with an unannotated netlist. So the designer gives you a netlist. You can't expect to find any hints there about the structure of the circuit. You also get a PDK, which is basically the foundry PDK, which could be Skywater 130, GF12, TSMC65, etc., or Intel 22 FFL. And then we go through a set of steps until we come up with the final output, which is a GDS2 of the design. Now, as part of this, what we do is we first take the netlist and annotate it. So we recognize structures within this. So from this netlist, we don't have a schematic or visual representation, but we recognize that there are some circuit blocks in here. So we might say this is an OTA, this is a switched capacitor network. We might say that there are some symmetries that have to be maintained. This is automatically done. Then you generate electrical constraints, which say that if you want to meet your performance specs, then your parasitic should be no larger than so much, etc. And at this point, you're now ready to start layout. So this is where you meet up with the PDK. We abstract the design rules, generate layout for the lowest level blocks, which we call primitives. And these are things like differential pairs or current mirrors. And then we progressively go up the design hierarchy to assemble the blocks and create the final placement, floor planning, and routing. So this is, in a nutshell, what the overall process is. Things have evolved a little since we first started, and I'll talk about that later. And we'll also have a demo that shows that. And basically, the quick cheat sheet on that is that the input is no longer just over here. We can provide inputs at multiple points over here. The reason we can do this is because we've built Align to be very modular. So you can bypass a module if you so desire. And this turns out to be especially useful for experienced designers. For example, we've been working with a lot of Intel designers, and they're like, we want to do our own annotation. We don't want auto annotation. So we cater to designers ranging from absolute amateurs who require a full annotation to professionals who say, well, we want more control, and we provide them the knobs to be able to do that.
I think that was a good design decision relative to how you constructed the package, the software package.
I think it helps to have people like Steve who had a lot of experience in the industry. So yeah.
I know from my experience at Oracle, and Michelle Lautis is on the call too, who I worked with at Sun/Oracle, but what we heard consistently from the custom design or analog design community there was the need for very such things, to have some degree of control when necessary.
Mm-hmm. Mm-hmm. Thank you.
As long as we're paused for a sec, could I just one quick comment? This is Dave. So in the spirit of open source, in an open source community and building or evolving tools, maybe one thought there is, if you guys provide instead of just skipping the annotation step, if you provide an annotation and then allow a designer to like confirm annotations or say, no, I want to re-annotate this part, but you got this part right. Seems like there's an opportunity there to capture information from a broad community and improve the tool.
So essentially at this point, we do allow the user to change the annotation, but we are not harvesting that information at this point because we are still trying to build up a user base among other things, but that's
yeah, it's just, from an ML perspective, right? Usually the limiting factor there is getting good labeled data. And so this would be an opportunity to add labels essentially.
Sure. Okay. So this is the entire Align team. You can see that it's a big project, a lot of people working on it, and they've all contributed. So even though I'm giving the presentation, I'm really just the figurehead. Okay. So let's become a little more concrete, and let's go with that switched capacitor circuit that I talked about a little while ago and see how we would take this through the flow. So we first start, although I've shown the schematic, we really start with a SPICE netlist over here. So it's really a set of lines of text that we start with. And from that, we need to identify these structures. So we first go through an annotation step, which would, for example, identify this OTA. And within this OTA, you would find that there's something like this. So the netlist doesn't have to be hierarchical in this form. It could be flat. We would identify this OTA. Then within the OTA, we would identify sub-hierarchies. So you can see that there's a current mirror, a differential pair, a load, etc. And this is the lowest level. At this point, we can actually do kind of algorithmic layout generation for these structures that we call primitives. So this is where we meet up with the design rules. We abstract the design rules into a JSON format, and we have a layer-specific gridding. So every layer has different gridding. We can talk about that a little more later. Based on this and the primitive structure, we can generate layouts for the primitives, and we can capture analog-specific constraints like common centroid or interdigitated structures, etc. Then you take these and you put them together into a layout for the OTA. So in this case, for example, the individual structures are shown over here and they're stacked together to create the OTA. And now you can put this into the larger structure. So the OTA is turned by 90 degrees and placed over here. There's a line of symmetry here, similar to this line of symmetry. There's a bunch of capacitors, which are these huge structures, and some switches that are over here. And presto, you have the layout for the switch capacitor filter. So the overall structure is something like this. And of course, there's a lot of there are a lot of finer details involved in being able to achieve this. So I'll go over these step by step fairly quickly right now. So the first step, like I said, is auto annotation and constraint generation. So it's basically the same thing. We're going to try and detect these hierarchies over here. And we have two approaches over here. One is if we have commonly encountered topologies, such as OTAs, we can have a library of structures and then use them to identify these. The other is if you have structures that you don't really want to kind of populate your entire library with, because it's very painful to do that, you can just identify array structures. And in the analog layout, whenever you find array structures and regularity, you typically want symmetry, matching, common centroid, etc. So there are some details over here, but essentially what we do is we use some kind of a machine learning approach. So we have a netlist, we represent the transistors and nodes in the netlist using a graph. And then we take this through a graph convolutional network to say, well, these nodes correspond to the internal nodes of an OTA, and the rest of them are outside the OTA. So that allows us to cluster this and create the hierarchy for the OTA. We've applied this to a few other circuits, and the confusion matrix basically shows that we are able to identify the components pretty well. However, like I said, this means that you need a large library. You need to have a training set for every type of structure, which is kind of painful. So if you look at some structures such as this, for instance, over here, you clearly have a repetition over here in of the comparator array and the R array. Similarly, over here, you have binary weighted capacitors. So there's repetition over here. And this is what leads you to understand that you're going to be doing some special layout structures. So the other thing also is that there are situations where you might have approximate matching. So in this case, you have a common gate LNA, a common source LNA. If you actually compared them one-to-one, you'd find that they're different, but they're actually close enough that you want to lay them out identically. And so we use the notion of a graph edit distance, which basically says, how much do I need to edit the graph of this left structure to reach the right structure? And there are good neural network solutions that allow you to find the graph edit distance. So by using these approaches, we can annotate specific structures, or we can discover hierarchies, and we can discover patterns that must be obeyed in the layout. So this, for example, shows the layout of an R2R DAC. And you can see that we identify an R2R array over here. The switches are kept separate from the array. Similarly, this is a 10-tap FIR equalizer. And you can see that there are 10 structures over here, which are essentially replicated. But the interesting thing here is that we have approximate matching here. So some of these current sources are 5-bit, some are 7-bit, but we can identify that they are kind of roughly similar. And when we lay them out, the 7-bit structures are in the middle, the 5-bit structures are on the outside. And this is a layout that's automatically generated by Align. So that's the annotation step. The next step is generating the primitive layouts based on design rules. So in this case, the philosophy is actually very similar to the classical lambda-based design rules. But of course, we know that lambda-based design rules don't work anymore. So the modifications that have been made are, aside from the main grid, there's a subsidiary grid, which is like an endpoint grid over here. We introduced the notion of Boolean constraints, and we allow layer-specific gridding. So for a bunch of commercial PDKs, as well as kind of fictitious or mock PDKs that we and other people have created, we've been able to abstract these into a relatively simple set of rules. And we end up getting layouts that are pretty competitive with human layout. Once we have this abstraction, then we want to perform cell generation. So if we have a larger circuit, we can identify structures that appear often. In this case, we are looking at differential pairs that appear in a bunch of circuits. So we would want to have a primitive that's called a differential pair. We have the ability to parameterize these primitive structures. So we can, for example, add a body contact or not. We can change the aspect ratio. If it's an array structure, we can have an n by m or m by n, or basically any other permutation of the array structure. We can use parallel wires to route R-sensitive connections, because these can degrade the transconductance, for example, of a differential pair structure. We can build common centroid interdigitated structures. We can change the number of fins and fingers for FinFET structures, change the active width, change the gate length. All of these are important for various circuits. And so we have a built-in primitive library that has these basic structures over here. These are the layouts for these structures. And we allow the user to specify new primitives as needed. Once we have this, the next step is performing placement, floor planning, and routing. And then basically, I'll kind of go through this very quickly. The idea here is that we perform kind of high-level placement considering global placement considering symmetry, alignment, matching, etc. We perform global and detailed routing considering symmetry, minimum length, etc. One of the important things we need to worry about, apart from symmetry and matching, are also things like multipath routing. So this is basically the idea that you need multiple parallel wires because you don't want to be resistance constrained. So all of that is taken into account over here. We perform power routing as well. We can create a mesh. We can try to make sure IR drop constraints are met, etc. In addition to this router, we have another router which has been donated by Intel, which is basically a SAT-based router. And essentially what it does is it takes all of these constraints and it creates Boolean representation of design rules. And then it says, well, if I have a structure like this with pre-routed structures, now I'm very constrained. This is where SAT excels. Now I can provide a very constrained space to SAT and give it relatively fewer options. A conventional algorithmic approach would struggle in this environment, but SAT actually thrives in this, and it's able to find good solutions. We also have some kind of machine learning built into this for performance estimation. And again, this is just a very quick overview because I want to hand it over to to Steve and to Sona to present other material. But basically the idea here is that as you go from schematic to layout, generating pretty layouts is not the objective. You want to meet constraints. So when you go from schematic to layout, you want to make sure that you meet your performance constraints. So basically what we do, we have various approaches. One of them is to use a graph neural network. There are a few other approaches as well. And based on these, we check at every step whether the performance is good enough or not. So when we generate a candidate placement for this, we have a fast estimator based on machine learning that checks whether the performance is good enough or not. If it's not good enough, it will give it a penalty. If it's good, it gives it a reward. And the basic idea is that that helps the search space and it helps us arrive at a good layout. Okay. I'll hand it over to Steve now, and he'll talk about the software architecture. Steve?
Okay, can you hear me?
Yeah.
Originally in the project, we started off with in a very decoupled manner when we built up the software. the flow, as we've seen in pictures before, is divided into these multiple stages. And each stage was developed originally more or less at one site. So we had the auto annotation stuff done at Minnesota, and the layout stuff was done at Temu, and primitive stuff was done at Intel and Minnesota. So since people had their own environments, we didn't really try to unify them very early. We kept this decoupled architecture around, and we used files to interface between the different stages of the flow. So we either used industry standard formats, usually simplified versions of them, or custom JSON schemas. And then we used Docker as a way to bring up each of the individual build environments, and then link them together that way. So that was a good way to start. But as, can you go to the next foil? That was a good way to start, but as the project matured, we sort of solidified on a decent common build environment, and we converted the whole project over to a Python-centric project, and all the C++ tools we put PyBind 11 wrappers around them so that we could call them directly from within Python. So the project then gets split more or less into these four categories of a compiler, a primitive generator, various utilities, and the place and route code. And there are two different place and route engines, this hierarchical place and route tool, and then this SAT-based solver. So each of these packages is now a Python package. They can be, we can use pip install to install the entire system, and each sub-package is more or less independent and can be used independently for different things if necessary. So the next foil, please, Sachin. And in terms of how we develop things now, we use GitHub for source control and team communications. We have lots of issues, lots of PRs around. We communicate in PRs about what needs to be fixed. The testing infrastructure is done using PyTest for Python and Google Test for the C++ code. Although a lot of the C++ testing now is done in Python because we have Python interfaces around it. We have a lot of check-in tests. We also generate coverage metrics. We have a continuous integration system. Every time we push to GitHub and a pull request, then we get a Circle CI run, which clones the repository, does this pip install, and runs PyTest and other tests, checks to see whether they pass, pushes to master cause more extensive tests to be run. So these pictures over on the right show that. Those are the Circle CI graphs. So for a push on a pull request, we just do a simple build in one of our build environments, and then we do some integration testing and unit testing. When we push to master, then we actually run it through a bunch of different build environments, different versions of operating systems and so on, to make sure that the system works. And we also run a lot more test content through. We have internal DRC checkers and mock PDKs that we have built to allow us to do all this testing on a public CI tool without having to worry about IP issues with PDKs. So I think that's it.
Do you want to talk about the alternative entry points too?
I think Soner has many foils on this, right, Soner?
Yeah.
Yes.
So why don't I kind of hand over to Soner and he'll talk about these alternative entry points. Before I kind of jump there, I'll just show a few kind of sample layouts that we've generated using Align. This is sort of the rogues gallery, and this continues. We handle multiple technologies as listed over here. And again, this list is also broadening over time. So I'll pass it on to Soner now.
Thanks, Sachin. I will keep my video off so that
I can use the whole screen more effectively. So I'll start with a few slides and then switch to a VNC to show the tool flow in action. And what I'll be focusing on is how we have been making use of Align at Intel, exercising on power management circuits in the 22FFL technology. So again, just a quick recap, right? Layout has become a chore. It used to be considered as an art form, but lately it's more of a chore than art. And on one hand, designers want very fast turnaround time. That is mainly because of the increasing gap between schematic and post-layout performance. However, design rules are making this harder as they get more complex due to multiple patterning and density rules. So is reliability is making it harder to close the layout due to this either self-heating or electron migration. And on the top right figure here, we can see some power management circuits that are pretty much mandatory in any modern SoC, CPU, GPU, or FPGA. And this figure is showing roughly in person by month the effort involved in creating the layout for these IPs. And why does it take so much time, right? The bottom right figure is showing a cartoon picture where analog engineers spend some time on deciding on the topology and the schematic sizing, and then hands off to mask designer. The first objective is really to, again, get post-layout parasitic feedback. So that's why these early iterations are quick and dirty. They are not DRC clean or not necessarily RV clean. But once there is more confidence that this specs can be achieved, then that's really when design rule and RV closure begins. And sometimes what happens is a significant violation could be found last minute, which requires either significant layout effort or even revisiting the schematic sizing to accommodate the changes. And despite its long history, as such noted, there's active research and development going on both in academia and industry, and thanks to DARPA. If you look at broadly, right, the previous work can be categorized as template-based and on one hand, and then also optimization-based. So template-based approaches can generate really good high-quality layout. This has been shown in silicon. However, it comes with a high coding overhead. On the other hand, the optimization-based techniques are a lot more significantly reduce this overhead, right, to device or device array generators that Sachin already mentioned. But then, of course, the question is, okay, how can we push the layout quality? So what we are pursuing is a practical and modular analog layout generation methodology, and particularly for advanced FinFET technologies. And one way we are achieving this is through these multiple entry points to accommodate circuits with varying performance needs. So what we call the vanilla align flow starts with this netlist, right? Which doesn't have any annotation, no constraints. And then the flow is fully automated, which goes through each of these stages and then creates a layout. And this seemed to work for what we would call non-critical circuits or that don't require special attention. And then for some circuits, this may require assisting the automation, especially the constraint generation, to improve the layout quality. And this is specified in a domain-specific language. This is a custom language that we have been creating. And it allows user to provide placement, routing constraints that are quite simple and quite a handful of these constraints to improve the layout quality. Yet there are still few very demanding circuits that require more control by the engineer. And this is what we call the entry point 3. What happens here is now in Python, the user or the design engineer can codify the placement and the route plan, which is also known as global routes, and then still utilize automated detailed routing, where this is still a big, hard problem, especially with advanced FinFET with multiple patterning. And if we take this to the extreme, there are these very few circuits that have high regularity. And here now, not only placement, but also the routing becomes quite straightforward, just using basically multiple for loops. And I will talk about some examples in the power management domain, but a good example here is a powertrain, which is really nothing but a very big transistor array, but it requires special consideration to reduce power density and also minimize IR drop. So in the demo, we will look at the latch comparator. This is a modified strong arm comparator, and we will try this on the mock version of Intel 22 nanometer FinFET technology. So if we just take a quick look at this circuit, you can realize the differential pair here. There's a cross-coupled inverters or cross-coupled NMOS and PMOS pairs, and then there are the inverters at the output. So these are some functional or matching sensitive building blocks of this circuit. And what we will look at is we are going to try running a full automated layout and then generate another version by giving some constraints to the flow. So at this point, I will switch gears to here. So everything starts with creating a netlist of that schematic that we see on this editor. If you want to also create a power grid, then we can create a setup file where we specify the name of the power and the ground nets. And this is sufficient to get started with using Align. So I'll just first start invoke Align, the schematic to layout, and then see the best solution it finds out of the box. And this is, you can see this took on the order of tens of seconds. Okay, I thought my Firefox was already open. Maybe not. Okay, sorry for this glitch. I think I can. There you go. Okay, so this is basically the layout generated right now, and we also saw on the PowerPoint slide. So if you look at this at the high level, what happened? Align did detect this matching sensitive pairs and then interleave them. So this we are here showing seeing the differential pair and then the cross-coupled devices and so forth. And it did basically generated this layout by trying to minimize the area and minimize the estimated wire length. Now, if you want to see more options, then one thing we can try is we can actually use our other interface, which allows us to see multiple choices or multiple options and then pick among them. So here, what I did is we asked Align, okay, show me your top 30 floor plans, basically. And here on the left, I will increase this a little bit. You can see an area and estimated wire length Pareto frontier, and there are several different floor plans that Align did explore. So this was the comparator 0 was the best solution that we saw. But then let's say maybe, for example, this is a particular solution where the clocking transistors or the pre-chargers are all consolidated, which would reduce the coupling. So to the trained eye, this lets you to choose a different floor plan. And if we are, let's say, happy with this, we can continue with the flow and then get the layout. Now, if we have basically what I would say strong opinions, or if we have preferences and want to have more control, then we can do the entry point number 2, where we can specify or provide some constraints to the flow. So here I'm just going to copy paste this and then run it. So what we did here is the first several lines, these group blocks are saying these are the transistors that we want to be interleaved or be placed in proximity. And the reason we define here is later on the line number 7 and 8, we are defining a vertical line of symmetry. So this vertical symmetric placement also improves match routing and reduces the offset. And the 9 and 10 specify some ordering in terms of top to bottom, where we want to place these primitives. There is on line 11, there's a multi-connection, which specifies, okay, for the tail or the common source of the diff pair, we want to use multiple tracks so that we can reduce source degeneration. And then the last one is an aspect ratio, which tells the line, okay, we also want to stay within this width over height range. Now with that, again, in under a minute, Align did generate the layout that we can see. So here you can, it should be visible that there's the vertical now line of symmetry starting from diff pair, cross coupled devices, and the output inverters are all the way on top. So I will go back to some results that we get using this flow. So here, this slide shows, again, flavors of comparator layouts. The top left is a manual handcrafted layout. This is created by an expert mass design engineer. And then you can see different flavors of this that were generated about a year and a half ago. And this was put on a test chip. We have the silicon results back. So in terms of the effort involved, so this top right figure shows how much it took to create the manual layout and then Align generated layout through different entry points. So here you can see there's basically 10x to 100x reduction in the design time. When we look at the manual layout, there's a lot of effort put into the initial getting base layers done, and then optimizing the interconnects to reduce the input referred offset, and then finally design root closure. So, but when we do entry point 1, as you just saw, it actually takes on the order of seconds, not even hours. Even given constraints, takes on the order of minutes. In the entry point 3, where we codify the placement in Python, that takes a little bit longer, but still within a day, it's able to turn around the layout and then do very fast iterations on it. On the bottom right, we see performance measured from 60 silicon samples. So the left figure is showing the input referred offset voltage, and then the right figure is showing the comparison delay. So there are, again, pros and cons. So if we compare the input referred offset, all of the generated layouts are still within the spec, but there is still some work to do to get to the level of manual layout. And also from the delay comparison perspective, so we can see that EP3 is very close to manual because it is actually codifying the exact same placement. So where EP2 has slightly larger delay, that's because putting these on a vertical line of symmetry increases the interconnect and therefore increases the delay. We also generated analog LDO using the methodology. Here on the left, you can see the manual handcrafted layout. So this LDO basically consists of an error amplifier, a compensation capacitor, and a big analog powertrain. And the right layout shows how generated layout through Align using entry point 3 and 4. So for the op-amp, we did follow the entry point 3 so that we can have the exact same placement as in the manual. And then for the powertrain, as is something I mentioned earlier, we did use entry point 4 simply because it requires special attention. So one is, for example, reducing the power density by inserting more white space or dummies in the array. And the other one is to maximize track utilization, because this is mostly an R-sensitive design. So the goal is to minimize drain and source resistance as much as possible, using as many tracks as possible. The top right figure shows, again, compares the layout design time of the manual effort and then the effort put into Align. And here again, we can see 7.5x reduction in the effort involved. And on the bottom right, we have some selected set of measured results. The left figure is showing the load regulation in terms of millivolts per milliamp. And here the generated layout is actually performing better than the manual. And on the right, we have the settling time with the maximum current step. Here, the generated layout is slower than the manual. And this is mainly because of the flexibility that mask designer has, right? So here you can see easily the blocks do overlap in the manual layout. But in the Align, we do actually follow rectangular building blocks that could increase the routing and also the routing parasitics in between. So to summarize, so far we have demonstrated it and get silicon proven results on power management circuits. And right now we are working on enabling the P-cell usage, basically leveraging P-cells for especially passive elements. We also did actually exercise a line on a more advanced FinFET technology, but we are still waiting for silicon to come back. And that was mainly using entry point 3 and 4. So in this case, we are now working on enabling more automated entry points on that node. And we are still, continuing doing research. One thing we are focusing on is defining a lean and formally verifiable constraint language, which can do some checks before the tool begins to make sure the given constraints are consistent, and then at the end to make sure the constraints are satisfied. Another line of research is generating RV clean layout. This is especially a harder problem in advanced FinFET. And again, using entry point 3 and 4, user has a lot more control, and it's a little bit easier to do this, achieve this, but there's still some room of improvement on the more automated entry points. And finally, we always try to improve the layout quality, basically push the performance with a smaller area footprint. And that's all I had to share.
Okay, thanks, Sonar. Just to clarify, the RV that Sonar had talked about is reliability verification, and that really is a very big deal for these FinFET layouts. Just to close, I want to kind of show this gallery of designs that we have over here. I think one of the strengths of our project is that we have academia plus industry. We have designers plus EDA people. Ramesh Harjani was a pioneer in analog EDA, but for the last 30 years or so, he's been focusing mostly on design. So we've had a lot of design advice from him, and also from Intel designers who've been actively testing our tools. We've had a set of chip tape outs. I think Sonar talked about some of the Intel tape outs. We've also been working closely with a USC design team. And this is a capacitive DAC that we taped out with them in June. This is a VCO that we taped out with them in March, and the silicon results looked very good. So we're going to be publishing those in the fall. And aside from that, as I mentioned before the call started, we are in a kind of a very close coupling with the Michigan team led by Professor Wentzlaff. And we are trying to generate these auxiliary cells that are required for their design methodology. So, and that's one of the kind of strengths of the modular nature of Align, that if, for example, there's a little piece that you like, for example, the cell generator, then that can be adapted for your use, or you can use the whole flow, or you can use any part thereof. So this pretty much completes our presentation. I think hopefully we are on time. Any questions, please?
You are on time. Thank you so much. Questions from folks? So I'll start with one. So it was an excellent presentation. It looks like some great work that that's ongoing between both partner universities and industry. I was just curious, do you have any other industry partners that are working with you aside from Intel, or?
At this point, our interaction is primarily with Intel.
Okay. Yeah. No, that makes sense.
Yeah, but I mean, we are sort of eager to spread our wings and also work with other companies.
No, that's good to know. I think I know, and since I've been in this role, I do hear different input from industry folks about wanting to accelerate the analog mixed signal design space. So I think there's a lot of opportunity here, right? And that certainly would be of interest. Any questions from other folks?
Yeah, hi, this is Thomas from Infineon. You mentioned your primitive cell library. How do you need to define that one? Is this simply, let's say, some Python code, or how do you define your layout primitives?
Basically, the layout, at the most basic level, the layout primitive is a netlist. But from that netlist, based on the design rules, you can construct a layout.
Okay, so the layout primitive is mainly the topology, so the circuit topology, and the layout generator is then doing the job afterwards.
Correct.
Okay, Thanks. Yeah.
Thanks, Thomas.
I mean, the primitives are designed, by align engineers, right? Using Python scripts in order to specify them, and that's a per PDK activity. So for example, for the 22 FFL circuits that Sanar was talking about, the primitives were built by figuring out what they should look like and then writing Python code using our self-fabric foundation libraries as a way of easily constructing and placing the transistors together. Is that a good way to describe it, Sanar?
Oh, definitely. And the idea there is to basically capture best known methods on that node, right? Because each technology has might have different effects, right? And especially as you go to more advanced nodes, for example, layout dependent effects become more prominent, and there are certain things or optimizations that you can encode on just device level transistor array level generators. So but again, that's compared to writing a generator for an entire circuit, that is still significantly less effort, but and a one-time investment per technology node.
Also, the belief is that the number of primitives are finite, as opposed to much at a higher level, they start becoming very large. So it's a finite set of primitives that we're working on.
The current built-in library is ballpark 20 primitives, but they can be extended and augmented as needed.
Mira from Silicon Austria Labs. I have a question. When you migrate from one technology to another, I mean, you're looking for a technology agnostic, let's say, approach. And so you're going from FinFETs to 65 nanometer TSMC, and then, to this new open source PDK. So what kind of effort do we're talking about? Because all these three technologies have different, let's say, layout methodologies that work, and it's not only abstracting or, let's say, scripting the PDK with Boolean algebra, but also the layout method that you use. So how much can you reuse, and what is basically development cycle? I mean, you went through it, probably it speeds up as you go, but still I'm just curious. Thank you.
So I can give a high-level answer, and then I'll pass it on to Sonar, because he's actually done this for a few technologies. So at the high level, one of the things that we do is we basically use the same method, kind of overall methodology, regardless of the node. So for example, we'll use a reserved layer model primarily, even if in 65 nanometers, you can take a turn in metal 1 and actually connect it that way. So we make that simplification because then that makes the methodology more generalizable. And based on some limited sample size that we've looked at, the hit in performance is not too bad. Sonar, can you talk about your experiences?
Sure. So we all talk about the primitive generator, right? So that's one piece of it. Piece of it is basically codifying this. And again, depending on the technology, if let's say that PDK offers P cells already, then the effort will be less, right? Then you don't have to draw every single layer. You can leverage those P cells. That would reduce the amount of coding involved. And the second big piece is engineering the grid, the interconnect grid. As Sachin noted, there's only unidirectional grid, and that is, it basically requires a decision of what pitch and width to be used for that technology. And typically there are recommendations as well, again, depending on the node, on what are some recommended wire widths, especially for analog or high frequency circuits.
Ramesh, do you want to add anything on 65? Your students have been working on 65.
I mean, the overall project is focused on FinFETs. So there's, accommodating that and the non-FinFET and bulk technology has a decision that has been made is to actually put the priority on FinFETs. And so there is a little bit more of a hit on the bulk technology, especially the unidirectional reserve layer issue. But in general, when we have done RF circuits with this, and they've actually been fairly successful in 65. We're using RF. We use the actual RF models for the transistor. So it's just been a viable technique. I think at this point, we're still really focused on the FinFET side and need a little more effort on the bulk side.
I should also add that a lot of the place and route work has been done by Professor Jiang Hu's group at Texas A&M. So they've basically been kind of handling this technology agnostic kind of approach as well.
Okay,
I just wanted to add, like in terms of effort, right? Again, depending on how demanding that node is, it would take probably 2 to 4 weeks to engineer the grid and create, codify the primitive generators. And again, there is some existing code, open source, which shows how to do this. So it's not going to be completely writing from scratch. It's more on take what is written and then maybe customize or modify.
And one of the things that we have on the GitHub repo is a set of mock PDKs. And by mock PDKs, these are things that are supposed to look like real PDKs, but they're all taken from the public domain literature. So we have a 12 nanometer PDK, we have a 22 nanometer PDK. These are, and when I say PDK, it's not a complete PDK. There are no SPICE models. These are basically layout design tools.
And am I right that your whole flow, beside maybe the support for P cells, is then completely independent from any Cadence solution or so?
The whole flow is independent from Cadence solutions. So even the we can use P cell-like structures and incorporate them, but the primitive generator basically does something similar to what a P cell would do. So in fact, one of the things that happens sometimes is that you want to import blocks that are black boxed. So you don't, it's a designer wants to use something that's generated from outside a line. So what we need to do is go through a step where we take that block and put it on the align grid. And once that's done, it can be used as a black box. And again, the Intel folks have done this extensively.
But when you now talk about that, you are currently working on some P cell support or more P cell support, therefore for resistors or passives and so on and so on. When you talk there about P cells, is this, do you mean this, let's say, skill P cells that you get from the PDK for Cadence there, or are the P cells only programmable cells, let's say, in more general?
Yeah, I was referring to Cadence, which also parameterized cells. So again, it is not required, right? You can still use the line as it is, right? I just noted that again for especially passives, it could, if they are available, right? And we also we enabled it to flow so that we can leverage them.
That you don't need to recode them again in Align,
exactly.
But you simply reuse them from the PDK that you get from the Fab guys.
Exactly.
Yeah, understood. Thanks.
I was just going to ask one question too, is relative to DRC, is there any dependencies on Mentor for that, or seems, I guess is the right word now, but sorry, but.
Steve, can you take that? Can you talk about the internal DRC checker?
Well, we've written our own lightweight DRC checker that checks to see whether the design meets the rules that were given to the tool in the first place. Now that is, not the complete set of tools. So you'll have to go, if you want to go fabricate it, you have to go put it into your design environment and then run through the flows. Now, whether that's Mentor or Synopsys or Cadence will depend on your manufacturer, right? So
of course.
Yeah.
And the hope is that through this gridding, etc., we are quote unquote correct by construction. But of course, you know that when the rubber meets the road, you want sign-off quality DRC.
And you want them, and the idea of our DRCs is to have them lightweight so that they're still fast, but they cover as many as we can. And what we add every once in a while, we need to add a few more, but it's pretty good right now in terms of if it passes our internal checks, it's likely to pass the sign-off ones.
Great, thank you. So we are just a little bit past top of the hour. Are there any final questions? If not, Sakin and team, I want to thank you for a great talk today, and also some excellent work. I'm really excited about looking a little bit at it myself. I was particularly intrigued by the pattern matching problem, knowing that from earlier lives in transistor circuit recognition from the timing analysis perspective. So great to see some of the work there, and looks like an exciting opportunity that you all have provided. So thank you much.
Thanks, Rob, and delighted to make this presentation to the group.
No, thanks. I think it was very good. So thank you all again for all the hard work and the time today too. Appreciate it.
Bye.
Thanks. Bye.
Bye-bye.
Thank you, guys.
Bye.
Bye.
Bye. Ciao.